Welcome back. So we have gone through our discussions on vorticity. We saw what different forms of or distributions of vorticity would be. We also looked into governing equation for vorticity. So now we get started with the last thing we looked at, which was Euler's equation. So rewriting our Euler's equation where we have a body force. So we ignore the presence of any viscous effects in the problem. So we are still looking at an ideal fluid. Now the advective term which is there in the problem, that's uj dou uy dou xj, or the u dot del u term. We know that this particular term can be written in a slightly more compact notation. We use this when we were working with vorticity, that this can be written as dou dou xi of uj square minus ui, or rather epsilon ijk uj omega k. So we can write the expression that we have in terms of gradient of u square minus u cross omega. This is the representation that we will get if we were to write the advective term. There is a way of writing the advective term in this particular form. Now, if I take my density to the other side, what this gives me, so I believe there is a factor of 2 here, I think. So u dot del u is gradient of u square by 2 minus u cross omega. So vector notation is this. So I can write that advective term now as dou dou xi of uj square by 2 minus epsilon ijk uj omega k minus 1 by rho dou p dou xi plus gi. This is just another way of writing my Euler's equation. Nothing has changed here in this form yet. So I can further write this as dou dou xi of uj square. I'll write as u square, the magnitude u basically being the magnitude of the velocity. So this is half u square. Now gi I can write as minus dou dou xi of gz, because if you remember that gi is g with a minus sign pointing in the third direction, or rather it's pointing in the negative third direction with the magnitude g. So the acceleration due to gravity can be written as minus gradient of gz. So if I bring it to the left hand side, I have plus gradient of gz plus 1 over rho dou p dou xi equals to epsilon ijk uj omega k. Now the term which involves pressure, if I have rho as a constant, then 1 by rho dou p dou xi becomes dou dou xi of p by rho. But we also encountered this new terminology of a barotropic fluid, where pressure is a functional of the density, in which case I can write 1 by rho dou p dou xi as dou dou xi of integral dP by rho. So, pressure is a functional of density, then 1 by rho dou P dou xi can be written as dou xi integral dP by rho. This is some function of the density. So, in either case, the point I am trying to make here is that as long as the fluid is barotropic, need not be constant density, the pressure gradient term 1 by rho dou P dou xi can be expressed as a purely as a gradient. So, Euler's equation for a barotropic fluid can be written as dou xi of half u square gz plus integral dP by rho is equal to epsilon ijk uj omega k. Omega, just to remind you again, is the curl of velocity or the vorticity. If density was a constant, this term would just become P by rho, because then it is integral of dP, which is pressure. If rho was a constant, it comes out of the integral and then integral dP becomes pressure. So, in which case that integral turns out to be just pressure by density. So, now here you have a gradient dou xi is equal to epsilon ijk uj omega k. So, we will consider a few cases. The first case we will look at is when the flow is steady. There is no explicit time dependence, in which case dou xi is half u square plus gz plus integral dP by rho is equal to epsilon ijk uj omega k. This term inside the bracket, I will define it as a function b, which is half u square plus gz plus integral dP by rho. For a constant density fluid, b becomes half u square gz plus P by rho. So, then for a steady problem, I have dou b dou xi is equal to epsilon ijk uj omega k. This is nothing but a statement of steady momentum conservation in absence of any viscous effects. There is no further assumption. Obviously, we have a statement regarding density, but other than that, the only thing we are saying is there are no viscous effects, the problem is steady. Now, if you look at this equation and based on the right hand side, if I dot the left hand side with u, so I take ui dou b dou xi, or to be more precise, I dot it with a unit vector which is along u. So, then I have ui dot epsilon ijk uj omega k. Now, this term, which is basically u cross omega, is going to be perpendicular to u. So, when I dot it with u, I am going to get 0. So, what this says is that the gradient of b along the unit vector given by the velocity field is 0. Now, we know what is the line which basically has at every point the velocity vector being the tangent. That is a streamline. So, what this statement says is that the function b, which is half u square plus gz, and if density was a constant P by rho, this quantity is constant along a streamline. So, if your flow was inviscid, your flow was steady and your system was barotropic, or if you make it more restrictive, if you say it is constant density, in that particular case, the function half u square plus gz plus P by rho, which is the Bernoulli function, is a constant. So, you measure it at different points on a streamline, you would get the same value. Going further, dou b dou xi is equal to epsilon ij k uj omega k. What if I dot this with the vorticity vector? This object, so omega cap I is basically a unit vector along a vortex line. At every point, that is a unit vector denoting the direction of vorticity. So, this quantity is u cross omega. So, this object is always perpendicular to the direction of vorticity. So, when you dot it with the vorticity, you are going to get once again 0, which means that Bernoulli function, repeating ourselves again, half u square gz plus p by rho is constant along vortex lines. So, if you have a flow that is steady, which is inviscid, and the fluid is barotropic, then the Bernoulli function basically is a constant if you move along a streamline or you move along a vortex line. There is also something slightly more exotic where this function is a constant. So, dou b dou xi epsilon ij k uj omega k. This term is u cross omega. So, if a flow was there where u cross omega was 0, which means u is parallel to vorticity, then this function b would be a constant everywhere. Now, that appears a little strange, because if you have a two-dimensional flow, then vorticity is perpendicular to the plane, right? Velocity resides in this particular plane and the vorticity vector is perpendicular to the plane. So, we are used to thinking of vorticity always being perpendicular in a sense or jutting out of the plane in which the flow resides. So, for two-dimensional flows this will never happen. For two-dimensional flows, the velocity vector and vorticity vector will never be parallel to each other. But it is possible for this to happen if the flow is three-dimensional. So, there can be flows which are known as Beltrami flows, where u can be parallel to omega, which means u cross omega is equal to 0, and thus the Bernoulli function is a constant everywhere. So, there are three cases that we saw, that if the flow is steady, obviously this is inviscid and barotropic. I am writing my B for constant density, but you already know that if it is barotropic, a general scenario, it will be integral of dP by rho. So, if the fluid is inviscid and barotropic and it was steady, then you would have the Bernoulli function being constant along streamlines, along vortex lines, and it can be constant everywhere if u and omega were parallel to each other. So, in general scenario, for a general problem, you can think of that you have a surface that is made up of streamlines, you have a surface that is made up of vortex lines, and the Bernoulli function is basically going to be constant along each of these lines as you measure it along. So, this is along each of these threads, you have basically stitched up a surface using vortex lines and streamlines, and along each of those lines the Bernoulli function is a constant. So, this was something where you started out making a steady assumption, and you still have a very restrictive criteria for it to be a constant. The restrictive criteria is that it should be either along a streamline or a vortex line, but it will, you cannot choose two arbitrary points in the flow and equate them to be equal for whatever we have learned. The only case you can do it is if you have these kind of exceptional flows known as Beltrami flows. But the scenario gets significantly simpler if you have an irrotational flow. An irrotational flow is where the velocity field has zero curl or vorticity is 0. So, going back to our governing equation was dou t of ui. So, I have not said anything about steadiness here. So, dou t of ui plus dou xi of b is equal to epsilon ijk uj omega k. This is nothing but Euler's equation. This is exactly a statement of Euler's equation. Now, if you say that the problem is irrotational, there is no vorticity in the problem, is 0 everywhere, then the right hand side becomes 0. The right hand side becoming 0 means that dou u dou t plus dou b dou xi is equal to 0. So, which tells us that I can think of this dou b dou xi to be a constant if the flow was steady. If the flow was steady, then b would be a constant everywhere if the flow was steady and irrotational. But what if the flow is irrotational and unsteady? I don't say anything about time dependence. Then I go back to this equation. I have curl of velocity field to be 0. So, going back to vector calculus, if there is a vector field that has 0 curl, then that vector field can be written as gradient of a scalar potential, because curl of a scalar gradient is always 0. So, if you have a vector field that has 0 curl, that means one can express that vector field in terms of gradient of a potential. Now, go back to this equation. If the flow is irrotational and has arbitrary time dependence, u will still always be a gradient of a potential because it is irrotational, it has 0 curl. So, going back to my Euler's equation, I can write ui as dou xi of phi plus dou b dou xi is equal to 0. Commuting the derivatives gives me dou xi of dou phi dou t plus b is equal to 0. So, we get a stronger statement. The statement that we get, that for irrotational flows, I have the following quantity to be constant everywhere. It does not matter if the flow is steady or unsteady. Obviously, if it is steady, then this term will drop off. But otherwise, you have this relation giving you what becomes a constant when you are looking at. So, instead of actually writing down an evolution equation and solving an evolution equation, what you have done here is you have basically related. So, what was, in other terms, what was actually a prognostic equation has become a diagnostic equation, that pressure at any point is related to the velocity and the velocity potential and the elevation, and this object is going to be constant everywhere in the flow. So, let us say in a given problem where z was the same and the problem was steady, then what you conclude is p by rho plus half u square is equal to constant if z was the same and the problem was steady. So, what you can then do is, if you know the velocity at two different points, you can automatically find the pressure between those 2 points. They need not be on the same streamline. That is the beauty of this, that because the flow is irrotational, this constraint or this condition is applicable everywhere. We have made assumptions. The assumptions that we have made are that the flow is inviscid. There are no losses in the problem. There are no frictional effects in the problem, because you can look at this and you can start to guess that this is like energy per unit mass. Each quantity has dimensions of energy per unit mass. So, in some sense this is also a statement of energy conservation. So, if you think in terms of losses, because there are no frictional effects, there are no viscous effects in the problem, it basically turns out to be a conservation of energy, which is how kinetic energy and potential energy and the work done by pressure are basically related to each other. But we have arrived at this from Euler's equation. So, this is our starting point for what we are going to do next. So, the next thing we are going to focus on from Euler's equation is discussing about irrotational flows. So, irrotational flows are flows where curl of the velocity field is equal to 0, which means the velocity field can be written as a gradient of a scalar potential. And there is a relation where pressure now gets related to velocity. Now, if the flow is also incompressible, so if divergence of u is equal to 0, then dou ui dou xi is equal to 0, which implies dou square phi dou xi square is equal to 0. So, what you obtain is that for irrotational flows that are also incompressible, which is known as potential flows, you have to solve for a velocity potential that satisfies Laplace equation. So, you now have two equations in the problem, del square phi equal to 0 and the Bernoulli equation relating pressure in terms of velocity and the velocity potential. So, u square there is actually dou phi dou xi dou phi dou xi. So, you solve for the velocity potential and using that you can compute what the pressure is. Significant simplification of a governing equation. All you need to solve for is the velocity potential. Once you know the velocity potential, you know the velocity field, and then you can find what the pressure field actually is. You do not need to solve for them simultaneously. So, potential flows are flows which will basically have 0 vorticity and it is also incompressible. So, why this becomes interesting? Because when you are looking at flows that have 0 vorticity, you just need to solve for this equation, but this equation is a differential equation, which means there is a boundary condition which you need to satisfy. You need to also solve this in conjunction with a boundary condition, you can't solve them arbitrarily. So, what are the boundary conditions that you need? The boundary condition is if you have, let us say, some solid surface. So, let us say this is a body, and for an example I will consider that there is a uniform flow past an object. So, the boundary condition we know should be no penetration boundary condition. So, the no penetration boundary condition is uk nk is equal to 0, n is the unit normal at any particular point. The normal velocity at any point is equal to 0. So, written in terms of velocity potential, this is dou phi dou xk nk is equal to 0. At any point on the surface, you can find the gradient of the velocity potential, its normal component should be 0, or in a simpler manner, you can say the boundary condition is dou phi dou n is equal to 0 on a stationary solid surface. If the surface was moving, then dou phi dou n should be equal to whatever is the normal component of the surface velocity. And if there is an imposed flow at infinity, if you say that there is a u infinity which is approaching. So, u infinity here let us say is x cap. There is some imposed flow that comes from infinity and it is flow past an object. So, in which case you will say that the velocity dou phi dou xi should approach u infinity x cap as distance approaches infinity. So, these are the boundary conditions that you have in the problem. If you are doing a problem where the object is translating and infinity is at rest, then in that particular problem you are going to equate dou phi dou n to the normal velocity on the solid surface. So, if you say the body is moving, then this is going to be equal to u body k n k, and dou phi dou xi should actually go to 0 as r goes to infinity. This is for a moving body in a quiescent, otherwise quiescent fluid, and this is flow past a stationary body. So, the scenario of solving your Euler's equation gets significantly simplified. You are solving for a Laplace equation for a velocity potential subject to these boundary conditions. Now, there is also one thing nice about this whole system. Whatever you have here, the expression for the velocity potential, the solution for the governing equation for the velocity potential, the boundary condition, this is all linear. Del square phi equal to 0 is a linear equation. The boundary conditions are linear boundary. If you have a boundary that is rigid, then your boundary conditions are linear, your differential equations are linear, which means the solutions that you are going to obtain, they should also obey linear superposition. So, everything seems great, but then if you start thinking a little bit, immediately you realize you started out from Euler's equation. Euler's equation is not linear, it is a nonlinear equation. So, there seems like there is a contradiction, that I am claiming that the velocity field, because the velocity field is gradient of velocity potential. The velocity potential can be obtained from a linear system, which means if I take two problems and superpose the two problems, the velocity field should be a linear superposition of those two problems, and that seems to be at conflict with what we understand from Euler's equation, which is a nonlinear equation. If you think a little bit more, you realize there is no conflict actually, because whatever we are discussing here is regarding the velocity field, but the solution is actually velocity field and pressure field, and the equation for pressure is half u square plus gz plus p by rho, and if there is an unsteady term, then dou phi dou t is equal to constant. So, the relation between velocity and pressure is nonlinear, as it should be. You have derived this from Euler's equation. So, the relation between pressure and velocity is a nonlinear relation, which means if you consider a problem and you superpose the velocity from problem 1 and superpose the velocity from problem 2, the pressure will not undergo a superposition. So, for the combined problem, the pressure field is not going to be a linear superposition of the pressure fields. So, which is what is now a consolation, because otherwise it would have appeared bizarre that without dropping the nonlinear terms, I am now trying to claim that the system has become linear. So, from the perspective of obtaining the velocity field, you can obtain all of this solving linear equations. So, this linear equation actually, if you think about it, didn't come from conservation of momentum. It came from a kinematic consideration and mass conservation. It came from the consideration that the velocity field is irrotational, which has nothing to do with conservation of momentum. It is a kinematic statement that there is zero vorticity in the problem. So, if there is zero vorticity in the problem and the flow is incompressible, then the velocity potential satisfies this equation. Nowhere did I use any connection or borrow anything from momentum conservation. So, those two statements, curl of u equal to 0 and divergence of u equal to 0, they are linear equation. So, automatically what you are going to obtain would be a linear equation. There are no surprises there. But the full solution is not just velocity field, there is a pressure field associated with it. So, once you obtain the velocity field, you need to obtain the pressure field, for which you need to go back to your Bernoulli equation. and that is a nonlinear equation. So, the entire solution, which is u comma p, you cannot superpose. Okay. So, this is something which is interesting and important, because we will superpose velocity fields and get the combined velocity field, and then what we obtain as the pressure field for the superposed velocity field will be different than the sum of the two superposed pressure field. So, the velocity field which is combined will be equal to the two velocity fields summed over, but the pressure field will not be a sum. This is a small but important point, because if you just focus on the equation and focus only on the maths behind the equation, you might be tempted to think that you are solving a fully linear system. That is true as long as all that you are doing is finding velocities and nothing else. And finding velocities does not require any requirement of looking at momentum conservation here. You are doing it purely based on irrotationality and incompressibility. These are the two things which basically work together to give you the velocity field. So, this is a significant simplification of your equations, and this allows us to actually solve flow problems where there is no vorticity. Now, you might ask that is that a good scenario to be in where there is no vorticity. Now, if you go back to your Helmholtz equation or the Helmholtz theorem, if there was no friction in the problem, what Helmholtz theorem told us is that if there was no baroclinic torque, if there was no friction in the problem, fluid particles which did not have any vorticity to begin with will always not have any vorticity forever. If I remind you that the equation for a barotropic fluid, this is what was the equation which was the Helmholtz equation, and the first Helmholtz theorem told us that if the fluid parcel did not have any vorticity initially, it would have no vorticity for any later time, which means if it was irrotational and there was no vorticity to begin with, there would be no vorticity in any time in future. So, that is basically what we are saying. Now, you can question that whatever we are ignoring here, which is the role of viscosity, does that play a role? And the answer is a big yes. But at this moment, what we are going to focus on is saying that go with us with this assumption that there is no source of vorticity that is there, viscous effects are negligible, and let us go ahead and try to find out what the flow field will look like. And then we will do a course correction. Then we will do a course correction to see what viscosity does. The other part which is very interesting here, that if you actually go back to your Navier-Stokes equation, so we are working with the Euler's equation, which is this. Now, the term that we did not write, that particular term was dou square ui dou xj square. That is the viscous term. And I said, okay, we will not look at the viscous term and we will just focus on Euler's equation. Now, here comes a surprise. Take that viscous term, dou square ui dou xj square. If you go back to your exercise problems from tensor, Laplacian of a vector field can be written as gradient of the divergence minus curl of a curl. So, dou xj of curl of u k. So, this is epsilon k mn dou u n dou xm. So, del square u is gradient divergence of u minus curl of u. Now, why is this interesting? If I am doing potential flow problems, what are the two things that we have? Divergence of u is 0 and curl of u is 0, which means the viscous force del square u is identically 0 for potential flows. Now, this is a remarkable result, that potential flows are exact solutions of Navier-Stokes equation. This is not stated often enough, But when we study potential flows, those potential flow solutions are also solutions of Navier-Stokes equation. This is an important point. Where is the catch? There is always going to be some twist, right? Otherwise, this is too good to be true. Now, an equation, I keep repeating this point, an equation does not come just with the, when you say I am solving an equation, it just does not come with the equation, it comes with the boundary conditions. So, Navier-Stokes equations are this, but then there are boundary conditions. Boundary conditions are no penetration boundary condition on solid surface and no slip boundary condition on solid surface. So, if you write down the tangential component of the velocity, that should also be 0 on solid surfaces. If you remember, we wrote this down, right, that uj delta ij minus ni nj, this also should be equal to 0. On a surface, if there is a unit normal n, then this quantity which gives you the velocity that is tangential to the surface, that should also be 0 if it is a no slip boundary condition. Potential flow solutions cannot be made to satisfy both boundary conditions. That will become an overdetermined system. It can only satisfy the no penetration boundary condition, but it will not be able to satisfy this boundary condition, which means this statement potential flows are solutions of Navier-Stokes equation has to be modified that do not satisfy the no slip boundary condition. So, there are various approaches, numerical and theoretical, which try to use potential flows and apply them to viscous problems, where the modification that is occurring is from a no slip boundary condition. So, you say the flow is potential everywhere other than the fact that near solid surfaces where you need corrections to the solution that take care of this particular boundary condition. But away from boundaries, they are exact solutions of your Navier-Stokes equation. So, this is an important point which helps us often in terms of understanding solutions of the full Navier-Stokes. So, now we have the potential flow equation del square phi equal to 0 with the boundary condition that dou phi dou n is equal to 0 on a solid surface. And far away, if there is an imposed flow, it goes to the imposed flow, or else you would actually have whatever is the other boundary condition at infinity. So, you apply one on the body surface, one at far away, because mathematically this equation is what is known as an elliptic partial differential equation. There are various equations which falls in this category, which comes from heat equation, magnetostatics, electrostatics, a whole bunch of family of equation which follows this. And there are various methods of solving this equation. So, we are not going to go through the different methods that are there. The easiest method, which probably is what you learn to begin with, is doing what is known as separation of variables. That you can assume the potential is some function of x times some function of y if you are doing it in 2D Cartesian, or if you are doing it in polar, some function of r and some function of theta. If you are doing it in 3D, then you will say some function of r, some function of theta and some other function of the other angle phi, the polar angle phi. You can also do transforms. You can do a Fourier transform and basically make this into an ordinary differential equation. Let us say you are solving for del square phi equal to 0 between two plates. So, you can basically do a Fourier transform in this direction, which is parallel to the plate, and make it into an ordinary differential equation in the direction y. That is another approach of doing it. Once you solve the problem, then you can come back and do the inverse Fourier transform. There is also, if you are doing, so all these methods, the first and the second one, they can be done in any dimension. whether you are doing in 2D or you are doing in 3D, does not matter. But if you are doing only 2D, so if you do 2D potential flows, then there is a method which is quite popular, which is using complex variables or theory of analytic functions. What that says is, if there is a function of a complex variable, so if you say z equals to x plus iy, you have a two-dimensional problem. And if you have a function of a complex variable f of z, then if it is an analytic function, it satisfies Laplace equation. So, it will basically be solving for Laplace equation. So, if you now define f of z as some u of x comma y plus I v of x comma y, then both u and v, these are going to solve for Laplace equation, and they are also known as harmonic functions. So, that basically gives you a tool of writing down a lot of different kinds of analytic functions, because the moment you have an analytic function, you know automatically this satisfies Laplace equation. So, that gives you a whole different way of looking at problems in 2D. So, I am not going to go through and individually derive these solutions. Separation of variable is something which is easy to get familiar with if you have not done this before. So, the best way to think of that if you are doing these problems is look at simple solutions. So, in Cartesian coordinate system, so I will more or less do these things as substitution. Rather than trying to formally write it down what is a series solution, I will do more like substitution. So, the first solution that I will take is phi is equal to some constant times x. As you can check that any linear function of the spatial coordinate is a solution of del square phi equal to 0, right, because it is a second derivative. So, if you have del square phi as a linear function of the Cartesian coordinate x, y or z, will always solve this equation. Now, we are not interested in the math of Laplace equation, we are more interested in the velocity field. So, given that we know what is phi, can we actually find out what would be the velocity field? So, u is gradient of phi, which means the x component is dou phi dou x and the y component is dou phi dou y. So, now you can plug it in. So, what do you get? Let us put a bar here to distinguish it, that the x velocity is u bar and the y velocity is 0, which says that I have a velocity field which is a series of straight lines where you have a uniform flow. So, a uniform flow is a solution of Laplace equation. Now, when I sketched out these streamlines, I said these are streamlines and basically I am writing down the velocity field from given that particular value of potential. Now, what would be lines of constant potential? Lines of constant potential should be lines of fixed x, because phi is equal to u bar x. So, when x is fixed, that gives me a constant phi. So, lines of constant x are basically lines of constant phi and the horizontal lines are streamlines. So, is it a coincidence that the streamlines and lines of constant phi have intersected at 90 degrees? We have already done this kind of a problem, right, that if u is equal to a constant and v is equal to 0, the streamlines are going to be parallel to the x axis. And here the lines of constant potential are perpendicular to the streamlines. So, is that a coincidence? So, we can check. So, we know that u is equal to dou psi dou y, v is equal to minus dou psi dou x, and u is equal to dou phi dou x and v is equal to dou phi dou y, which means if I now write d psi is dou psi dou x dx plus dou psi dou y dy. So, along a fixed psi, when psi is held fixed, what do I have? I have dou psi dou x dx plus dou psi dou y dy along a fixed value of psi is equal to 0. The LHS is 0. If I fix a value of psi, then d psi is 0 and I get this, which means I will have dy dx along a fixed value of psi is dou psi dou x minus dou psi dou y. Now, what is dou psi dou x? Minus v. So, this becomes v by u. So, I have dy dx along line of constant psi is equal to v by u. You do the same exercise for phi. D phi will be dou phi dou x dx, dou phi dou y dy. So, along a fixed value, for a fixed phi, I will have dy dx for phi being fixed is equal to minus dou phi dou x by dou phi dou y. Now, what is dou phi dou x? U. What is dou phi dou y? V. So, what do you have here? Dy dx for fixed psi multiplied by dy dx for fixed phi is equal to minus 1, which means the lines are orthogonal to each other. So, stream lines and potential lines or lines of equipotential lines are orthogonal. This exercise we did for 2D, where you can define the stream function without any ambiguity. In 3D, obviously you have to realize that there are two stream functions. We discussed this, that you have to come up with two stream functions to do the process, but you will have the streamlines and potential lines are going to be orthogonal to each other. So, we saw one of the solutions of being a uniform flow. The other potential, so you can work out what are the various solutions of Laplace equation, and I am going to use them and work with those solutions. So, the other solution for that is going to we will work with is phi is equal to some ln r. So, phi equal to ln r, if you write down what is your Laplace equation in polar coordinate, 1 by r dou r dou phi dou r plus 1 by r square dou phi or dou square phi dou theta square is equal to 0. That is your polar Laplacian or cylindrical Laplacian, I am writing in 2D. Now, you can see that if phi is equal to log r, then this becomes r times, so if I put a constant here q, then this becomes q by r, dou r of q by r, right. So, r and r cancels out and this becomes 0. So, this is by substitution I am showing you that q ln r is basically a solution of Laplace equation. R is the radial coordinate. Now, what is the velocity field? So, there will be a radial velocity u r, which would be dou phi dou r, and there would be an azimuthal or tangential velocity which will be 1 by r dou phi dou theta. So, dou phi dou theta would obviously be 0 because there is no theta dependence in the potential, but this is going to be q by r. This is a radial velocity that is increasing as you go towards the origin. So, you have a velocity field that is q divided by r cap. How would the streamlines look like? So, streamlines are all going to point either inward radially if q was negative. If q was positive, then they would be radially outward. And if you were to compute u dot a cross sectional area, like you consider a circuit, so in 2D it is just a line. So, if I just consider that particular closed line over a closed contour, then this would be q by r d theta at a given value of r. So, at r equals capital R, theta goes from 0 to 2 pi, this gives me 2 pi times q, and this has units of volume flow rate per unit depth. So, what you find is irrespective of any particular radius, you can choose any radius, the volume flow rate per unit depth is given by 2 pi q. So, you can redefine it and put a 2 pi here, in which case this becomes q actually is the volume flow rate per unit depth. So, this is known as a sink flow, this is a source flow. In the same fashion, you have basically fluid rushing out or fluid coming in. These are again two canonical potential flows. There is a sink here and then here there is a source that is there in the problem. So, this is the second class of potential flows that we saw. So, we will look at few more class of potential flows and then try to use them to solve our problem. So, I will stop here.